Today, I'd like to talk about neural networks, specifically a type known as multi-layer perceptrons. So let's begin with a clear definition. Neural networks are a fundamental type of machine learning model. And what's particularly interesting about them is that they are intentionally designed to mimic the way the human brain processes and interprets information. Think of them as computational approximation of human cognition. This analogy isn't just poetic, it's quite literal in the architecture and the way data flows through the model. Now, let's talk about purpose. Why do we care about neural networks? Well, these models are incredibly versatile. They revolutionize how we approach tasks like image recognition, where we can identify objects in photographs with impressive accuracy. They're the backbone behind language translation, helping bridge communication across different languages. And they're widely used in predictive analytics, from stock market predictions to diagnosing medical conditions. Essentially, neural networks are adept at taking large, complex data sets and making sense of them in a way that traditional algorithms often can't. The key to their success lies in their structure. A neural network consists of multiple layers, typically an input layer, hidden layers, and an output layer. Each layer is made up of nodes, or what we refer to as neurons. These neurons are interconnected, and each connection has a certain weight as data passes through these layers. The network applies a series of mathematical operations to identify patterns and relationships within the data. Here's where it gets interesting. Through training, neural networks learn to adjust these weights to minimize error. Think of it like a musician fine-tuning an instrument to hit the right notes. Similarly, a neural network fine-tunes its internal parameters to produce accurate results. So, in summary, neural networks are powerful models designed to emulate the way the brain interprets information. They serve a wide range of purposes, and they consist of interconnected layers of neurons that work together to find patterns in data. Now that we have a foundational understanding of what neural networks are, let's dive a bit deeper into their structure and components. A neural network is organized into three main layers. These layers are essential to how information flows and how the network learns from data. First, we have the input layer. This layer is quite straightforward. It's the entry point for all data coming into the network. Think of it as the doorway. If we're dealing with image recognition, for example, the input layer would take in pixel values from an image. Essentially, it's the layer that receives raw data, and it passes this information forward to the next layer. Next, we have one or more hidden layers. These layers are where the real magic happens. In these hidden layers, the neurons process the input data through a series of mathematical transformations. You can think of each hidden layer as a set of specialized workers, each performing a specific task to extract patterns or features from the data. Depending on the complexity of the task, we may need several hidden layers, each refining and building on what the previous layer has learned. This is why it's sometimes referred to as a deep neural network, deep in the sense of multiple layers. Finally, we have the output layer, which produces the final result of the network's computations. If we go back to our image recognition example, this output layer could represent a set of probabilities, indicating the likelihood that the image belongs to one category or another, like a dog versus a cat. Now, it's important to note that each of these layers consists of nodes, which we call neurons. These neurons are where the processing takes place. Just like in the human brain, these neurons perform basic operations. Essentially, they take in information, perform calculations, and pass the result on to the next neuron. What connects all of this together are the connections between neurons. These connections are not just pathways, they have what we call weights, which determine how much influence that one neuron has on another. During training, the network adjusts these weights, allowing it to learn patterns from the data. So, to summarize this section, a neural network has three main layers: the input layer, hidden layers, and the output layer. Each of these layers contains neurons, and these neurons are connected in a structured way that allows information to flow and be processed effectively. Now that we've covered the structure of neural networks, Let's talk about how these networks learn. This is perhaps one of the most fascinating aspects of neural networks, the learning process itself. Neural networks learn by analyzing large datasets, and this is a fundamental step known as training. During training, we feed the network what we call training data. This dataset is crucial because it contains both the input data and the corresponding correct answers, or labels. For example, if we're training a network to recognize handwritten digits, the training data would consist of thousands of images of digits, each labeled with the correct number. But how does a neural network go from simply receiving data to actually learning from it? This is where the network's learning mechanism comes into play. As the data passes through the network, each connection between neurons has an associated weight, a number that determines how much influence a particular neuron has on the next one. Initially, these weights are set randomly. As the network processes more data, it adjusts these weights to find patterns and relationships. The goal is to improve accuracy over time. Let's add another piece to this process, the feedback loop. As the model makes predictions, it compares those predictions to the correct answers provided in the training data. When the network gets it wrong, it receives feedback in the form of an error signal. This error signal is then used to adjust the weights in a way that reduces the error in the next prediction. This loop continues iteratively until the network achieves an acceptable level of accuracy. To put this into a more relatable analogy, think of it as learning to drive. When you're first starting, you might make a lot of mistakes. Maybe you brake too late or turn too sharply. But with each mistake, you receive feedback, either from your instructor or from the car itself. Hopefully not the hard way. As over time, as you get more practice and receive more feedback, you naturally become a better driver. In a similar way, a neural network improves as it processes more data and adjusts based on the feedback it receives. To wrap up this section, a neural network learns by analyzing large dataset and adjusting its internal parameters, its connections, based on that data. Through a feedback loop, the network continuously fine-tunes itself to minimize errors, becoming more accurate with each iteration. So far, we've discussed what neural networks are, their structure, and how they learn. But you might be wondering, how do we actually use these networks in the real world? Well, the applications are vast and varied, touching almost every industry you can imagine. One of the most well-known applications is image recognition. This involves identifying objects within images, something we see in technologies like facial recognition used for unlocking smartphones or tagging friends on social media. But it doesn't stop there. In autonomous vehicles, for example, neural networks are used to identify and classify objects like pedestrians, other vehicles, and road signs, enabling cars to make decisions in real time. Another significant area is natural language processing, or NLP for short. Here, neural networks help computers understand and generate human language. This is what powers chatbots that provide customer service, or language translation tools that allow you to convert text from one language to another in just a few seconds. Neural networks in NLP have been instrumental in advancing human-computer interaction. Moving on to a field where the stakes are higher, let's talk about healthcare. Neural networks are being used to predict patient outcomes, diagnose diseases, and even personalize treatment plans. Imagine a model that can analyze a patient's medical history and predict their risk of developing a particular condition. This allows healthcare professionals to take preventive measures early on. Neural networks are also helping radiologists by analyzing medical images to detect anomalies that may indicate diseases like cancer. And the advancements here are saving lives every day. Lastly, we can't forget the finance sector. Neural networks are extensively used in forecasting stock prices by identifying patterns that humans might overlook. They're also used in fraud detection, where they analyze transaction data to flag any suspicious activities that could indicate fraud. These applications not only save companies money, but also help protect individuals from financial crimes. So, in summary, Neural networks are at the heart of some of the most groundbreaking advancements in areas like image recognition, language processing, healthcare, and finance. They are enabling machines to perform tasks that once seemed impossible or highly impractical,